right, so we've been looking at confidence intervals as a way to do inference, right? We're interested in a population and some parameters, usually a mean or a standard deviation, or a mean or a proportion, and based on that, we can make an interval that describes what the likely values of those proportions are. And we're going to transition today to looking at another way of doing inference, right, which is hypothesis tests, right? We have certain hypothesized values that we're interested in. How do we assess those with the data that we have and account for just the randomness that's in the system from taking a sample? So in our confidence intervals, formulas that we've primarily seen, we've had this scenario where we have a population and we're interested in parameters like the mean or the proportion that are in there, and then we have our sample coming from that, and then we have some different sample statistics. In the population, these are referred to as parameters. They're the characteristics of the population, and we can have X bar as a sample average, or P hat as a sample proportion, sample average, sample proportion. And we're going to make inferential statements going up that way, and based on the probability theory, distribution theory, we determined that we could do a confidence interval for the mean as X bar plus or minus some t-value times an estimate of the standard error, SO of the square root of n. And where this thing was based on a t-distribution, and whatever level of confidence we want. And this one, we use a t-distribution. We have this thing called degrees of freedom, which is one less than the sample size. There's probability theory, that's how it works out. And the t was a little bit wider than the normal to express the extra uncertainty from estimating that standard deviation instead of knowing it. We had a comparable formula for estimating a proportion. Right? So we have a confidence interval for a proportion. There's a sample proportion is at the center, plus or minus some value, and the distribution theory works out so that we typically use normal for that. Even though we're going to estimate the standard error with the p hat involved in it, it's still tradition and justified to use normal because it's some normal approximations. And the standard error associated with p hat is related to the binomial variance. And so there's a p times 1 minus p over n. But we don't know those, so we're going to just plug in the sample values there. And so both of these we get intervals, and those intervals basically give us an indication of where the likely values of the parameters are. Right? So if these are 95% confidence intervals, then we would think that 95 out of 100 times the intervals we make this way should really cover the truth. So they give us a pretty good accurate indication of where it is. It reflects both the center, where our data estimates are, plus or minus some margin of error. And so that gives us some information about mu. The other way that this is done in hypothesis testing, right, is to start out with a hypothesis about what you think these things are. Right? What is the population mean, or what is the proportion? And so we can form some hypotheses about the parameters. And we usually form a couple hypotheses in this. One H0 is called the null hypothesis. We're going to do the other one is going to be an alternative hypothesis. And the nature of these is not quite the same. The null hypothesis often stands for no effect, or no difference, or just status quo, everything as it was before. So this one often ends up meaning no difference, no change, or equivalent to what is believed to be the general population value. The alternative is often that there a claim that there is some difference, that the parameter is really bigger than that, or less than that, or just different than the null value. There is a difference. Okay. Or there is a change, and there's claim that there's possibly a benefit or a harm relative to the null up there. So this could be related to harm or benefit from a treatment. This could be all the conditions you're testing, all the experimental conditions have no effect and everything's the same. This one could be that some of those conditions are better or more advantageous than other ones, right? And so if you're looking at some of these hypotheses, it can be adapted to any number of conditions. So let's say you're looking at a drug study with individuals who have high blood pressure. There's systolic blood pressure. There's diastolic blood pressure for different blood pressure measurements, right? And so there could be two groups. There could be a treatment and a control group. And we could look at average blood pressure in these two groups, some that are under treatment, some that are under control. So there could be an average under the treatment group. There could be an average under the control group. You could pick one of these particular blood pressures, like systolic blood pressure, right, if these are the averages of that one, say. And a null hypothesis would be set up saying that there's no real difference between these groups. So a null hypothesis about these parameters, right, is just going to say that these two things are equal. Right? Or perhaps that you phrase it as the difference between these two things is zero. And you can either subtract treatment from control or control from treatment, but under the null hypothesis, it's still no effect. Right? The alternative, right, in this case, if the drug is supposed to lower high blood pressure, then we could say, that the treatment mean should be less than the control mean. And that would imply that the drug lowers blood pressure. So I guess this would imply that MT minus mu sub T minus mu sub C would be less than zero. You might phrase it the other way, UC minus mu T is greater than zero, but consistent with that, one being bigger than the other. And so we're going to get data, right? And so we're going to get a sample. There's going to be some average for the treatment and some average for the control. We can look at those. And they might be close together or not, but they'll probably be different. We could look at the difference between the two averages. Right? And we're going to see if, under which of these two hypotheses, whether it looks reasonable to continue to believe that maybe they're equal. But if the difference is big enough, right, is negative enough, we're going to want to say, no, because of what we've seen in this sample, this null hypothesis, it just is not plausible anymore. So if it's far enough away, then we're going to give up on that null hypothesis and conclude that, yes, the drug is better. Right? But then the question is, how far away does this actually have to be from equal? How far below zero is it before you're able to convince people that it really is clear that the treatment average is smaller? So the question in hypothesis testing really is how small does x bar t minus x bar c need to be before you reject the null hypothesis. And conclude that the alternative, which is what you would hope would come out of this drug study, if that's the intent, is to lower blood pressure. And conclude that the alternative is right. So how small does it actually have to be for that to work? And it's going to depend on the sampling distribution of this statistic. Right? If we see a difference of 5 units of blood pressure, well, that's not maybe that big of a difference. But if it's based on a really big sample, then it probably is actually lower. On the other hand, you could see it have a difference of 20 units there. But if it's based on a really small sample, it might not persuade people to believe that it's really that magnitude, because the standard error could be quite large. Yeah?
So if you reject the null hypothesis, does that mean that the alternative is right? Or
It
do you have
means
them
that,
proven
in this hypothesis testing, we're never really completely sure of anything.
Okay.
Or just like confidence intervals. You can have a very big sample and a very narrow confidence interval, 95, 99% confidence interval, but there's still some chance that you'll miss. Because in random sampling, sometimes you get an unusual sample. You get one that's very larger than expected, or very smaller than expected, and the confidence interval could just be off. And in this hypothesis testing, you can get unusual values that's just in a random sample. 95 times out of 100, it's not so unusual, but there's that, you do testing and enough projects, eventually one is going to get you some funny result. And so you can reject this one, and there's a chance that will be an error. We'll talk more formally about those errors. Right? There's a chance of rejecting this one when it's true and that error, and there's a chance of making the other error, that you can't reject this one when that's true. And both of those things are concerns. So we'll be a little bit more formal about that. In the second day we talk about hypotheses, those error rates, significance levels. It kind of has a corresponding to the confidence level. Right? We're going to have a 5% significance level that'll kind of have the same error interpretation as missing 5% in confidence interval. So there's a close connection there. Right? But we can think of a number of other examples. Right? So what we're going to look at today is kind of a randomization approach to this. Right? So the way that this really works is that we have some hypothesis about the population. And then we get some data that leads to a statistic. I guess I should say hypotheses about the population. We usually have a null and alternative statistic. And we're going to look, is our statistic value consistent? Is the statistic value consistent with the null hypothesis, or more consistent with the alternative? Right? And if the statistic is inconsistent with the H0, right, but if inconsistent with the null hypothesis, but consistent with the alternative, we say that we reject the null hypothesis in favor of that alternative. And so judging that level of consistency becomes an issue. Right? And so to do that, we're going to look at the issue of how do we decide. So let's look at one example that's on the handout. Does everybody have a copy of the handout? Yeah, it is here. Not kidding. So we're going to look at this data set. Right? This is a data set on admissions to an intensive care unit. And so there's a number of patients, 200 patients in fact. These are their ID numbers. And there's ages, sex, male, female encoded there, race, and other things, systolic blood pressures, and so on. And if this is a random sample of individuals coming into an ICU, we have their age recorded there. And so we're going to look at the ICU is there. There's all these different variables there. You summarize the attached ICU, so it makes this calculations work nicely. Then the average ICU age there is 57.55. So the sample average is this 57.55. Right? We're going to imagine that some hospital administrator or somebody says that the average age of the people going into the ICU is 50. So claim that we make average age is 50 years old. That's going to be their general claim about the general population, what they think is true. What are they basing that on? Maybe they had past experience, maybe that's just their impression. Maybe that's the average nationally for the state of California or something. And so that's the age that they think it is. So a null hypothesis is going to be that the average of the population is 50. We're just going to take an alternative that says, no, that's not true. Not true. Right, the average is not 50. Some hypotheses are just, is it that value versus not? In many real applications, you have in mind a direction. Is it bigger or is it smaller? Kind of this one-sided alternative that makes sense. Right? So we've observed, based on these 200 people, we have an average of 57.55 years. Based on that value, should we reject the null hypothesis and conclude, no, 50 is really wrong? It's not. That's not actually the case. It's different. It's more like 57 and a half. Right? Do you reject? Well, put on a number line. Right? So here's 50. Here's our null hypothesis value, and for mu, and we've observed x bar 57.55. This is years. And certainly away from that, and it seems like a fairly big number. But it will depend on the sampling distribution of x bar. what is the sampling distribution of X bar if the null hypothesis is true? So if this is true, if H0 is really true, what type of values of X bar would we see anyway? There's kind of two scenarios. One is that this distribution of X bar is really quite tight. Right? It's generally normal because flow systolic blood pressure in a population is pretty normal. This is the group that's going to the ICU, so maybe it's not completely normal, maybe it's skewed with some very high values for people that are there for blood pressure issues. But you average together 200 and it's probably pretty normal. Is it like this? Right, the distribution of X bar? If that's the sampling distribution of X bar, right, our 57.55 seems really unusual, right, very extreme. Right? On the other hand, if the sampling distribution of X bar was more flat, right, well, it's still kind of out there, but it's not quite as extreme. Right? It's not, you know, way out beyond the 99th percentile or something under that sampling distribution. Right? And so we translate into this question about do you reject? Have you gotten a value in your data that would be really surprising, very unusual if the null hypothesis is true? So we're going to reject the null hypothesis and the value that's claimed there if our observed X bar is quite unusual, is very unusual. If the null hypothesis were true. So we're going to calculate the probability that we would actually get some value that big or bigger, get something at least that extreme under the null hypothesis. And if that probability is really quite small, then we've seen a surprising result, we've seen something that's unusual. And you know, if it's this narrower curve, then something like that just doesn't happen in a realistic setting. And therefore the basic underlying, you know, hypothesis that it was that was the average becomes pretty unbelievable. Now it might be that we've got the really unusual sample and it really is here, but we happen to get just a bizarre sample that gave us a big average, but it becomes pretty unlikely, pretty convincing that it's just different. And so one way we can look at that is called randomization. We can essentially kind of bootstrap averages under the assumption that that null hypothesis is true. Right? So suppose the average age is 50. Is that plausible or not? Right? Well, here is the histogram of the ages in the sample. You know, 50s, 60s, 70s. 80s maybe are quite common, but there's this little group down here that are in their teens and 20s that happens to come in for different reasons. The 57, there's the 57 average. Right? This next one, there's the 50, the claim. Right? You can put little titles. The blue is the hypothesis value, and the red is the X bar. Is that X bar too far away for us to believe that, you know, the average is 50? You can look at the actual values. These are the actual ages, these actual numbers. This is a histogram of the actual numbers. Make a stem and leaf plot. Right? You get a nice stem and leaf plot that kind of mirrors that. Some people in the sample are 91, 92, youngest is 16, 17, and so on. Always good to kind of look at the data. Right? What's the sampling distribution of X bar? Right? What should the sampling distribution of X bar be? Now we know from some probability theory, kind of the stuff we do with confidence intervals. Right? What is the sampling distribution of X bar? Well, X bar is approximately normal. by the central limit theorem. And under the null hypothesis, right, we know the mean, right? Under the null hypothesis, u sub 0 is an average age of 50. Now the standard deviations, s over the square root of n, or sigma over the square root of n. We don't know that, really. We could take the sample standard deviation, and that's over the square root of 200, because it's our sample size. So it's something kind of like that. So if we can actually draw a curve, right, that represents that sampling distribution. So what does that look like? We can draw a little histogram that shows you where the likely values of x bar would be if the null hypothesis is true. So I'm going to set up some x values. Now my ages go 16 to 91. That's pretty wide, right? But x bar isn't going to be at 20, and x bar isn't going to be at 90, right? It's going to be closer to the middle. So I'm going to set up a little sequence of values going from 40 to 80. Those values are numbers, 40 to 80, going by tenths, so somewhat dense. If we plot the density, well, let's do the second one first. Right? This d norm is the density of a norm. So this is the height of a normal curve at these x's with a mean of 50 and a standard deviation that's s over the square root of n. Right? That plot is here. Right? That's the plot of the distribution of x bar. The red line, or the line at 50 is right here in the middle. If I generate that curve at 50, it should be right there in the middle of the normal. Where's my red line? Right, my red line is at the actual ages. It's out here. Right, that 57 is outside what's plausible, right? Because it's very, very unusual to get out here. Right? Sub. So if this had been the truth, we wouldn't have likely to get out here. If you looked at it the other way, and looked at the sampling distribution around 57, essentially we use that area to make our confidence intervals, right? We looked at kind of this 57 plus or minus a couple standard errors, kind of represented by that distance, and made a confidence interval. And if we made confidence intervals, as confidence intervals wouldn't include 50.
So how do you determine then, or which one to use, or do you combine them?
Well, so for the hypothesis test, we focus on this one centered at the 50, right? We assume that if the null hypothesis is true, right, our sampling distribution of x bar should be close to here, and then we're going to calculate the probability of seeing something, a 57 or more, as a probability, and if that's really small, it means that we're out here a long way away, right? So today we're going to simulate averages. What would it look like if we simulated data, kind of like a bootstrap, but centered at the null hypothesis of 50, right? So we're going to, sometimes this is called the randomization distribution or the null distribution of x bar. The sampling distribution of our statistic under that assumption. Right? So let's generate 1,000 bootstrap samples, and I'm going to save the averages in something just called boot. And to generate each bootstrap sample, I'm going to sample from my original ages. Oops. I'm going to adjust the data here. Right? So our original data is not centered at 50, right? It's centered at 57. But if I shifted everybody over, kind of artificially, to make the sample consistent with 50, it would mean moving everybody over, right? This thing, this new thing called age 50, is going to take my age and subtract its actual mean, right? So that the average of age minus its mean is just 0. And I'm going to add 50 back in. So I'm going to shift everything over, right, to an average of 50. You can also say this is its average age, and I'm going to take 50 minus the current mean. And so that's going to shift everything down by an average. So that my ages, kind of artificially, are moved toward that lower point, right? So if I do this adjustment, I take the average of those. This age 50 variable now is centered at 50. A little artificial, but it's kind of a shift. So now my bootstrap is going to take a sample of those adjusted ages. There's 200 individuals, so I'm going to sample 200 with replacement to get another kind of little variation and take the mean of those. So my bootstrap does that. Right? Now the histogram of my bootstrap averages looks like that, between 40 and 60. I put my red line there. My blue line actually at the hypothesis of 50. Right? My bootstrap averages are all, around that 50, like we would expect them to be. But the red line is completely outside of that. Right? So the bootstrap samples, they're about equally split between above or below 50. 50% or so are above, 50%, 49% or so are below. Kind of rounding takes care of that other part. But if you look at how many of these bootstrap values, see the bootstrap values are a whole bunch of values, right? They're, they say the first 10 averages. Our numbers there are kind of around 50. But the actual age of 57 is actually bigger than all of them. So the probability, so in this simulation we've done it 1,000 times. So we've done 1,000 simulations to do this randomization assessment. We adjust the data to be consistent with our null hypothesis of 50. To do that, let's call it a y. We took our x value and we took 50 minus the average of the x's. That's another way of writing that formula. So that the average value of y is, of our y value is 50. And then we took a bootstrap sample. There's actually sample n times, it's 200 in this case, from our 200 adjusted ages to be consistent with the null hypothesis. That was sampling with replacement so that we get a little bit of a variability in there. And we calculate the y bar in the bootstrap sample. Say we call it y bar b for the b bootstrap sample. In the other things, I kind of put a star on there to indicate it was kind of simulated artificial data. And then we're going to compare the distribution of the y bars under that simulation consistent with the null with what we actually got. And then compare the y bar star distribution to our original x bar. And if x bar is extreme, if it's out the tail, extreme among the 5% or 2.5% or 1% biggest, it's pretty unusual. In this case, it's bigger than all of them, so it's kind of way beyond that. Right? If we have a sampling distribution, if here's our y bar stars, if our x bar, is kind of out in the extremes, if x bar is out here, it's out in the tails. So this is centered around the u sub 0, the null of 50 in this case. In the tails, then we're going to reject the null hypothesis. And conclude that the average probably is not 50. The evidence is strongly suggestive that it's not 50, and you should rethink any type of planning or decisions based on that assumption. If, on the other hand, X bar is closer, so this area out here in red is called the rejection region. Out here, we reject H0, and X bar is in this rejection region, or R rejection region. On the other hand, if X bar is in here, we're not going to reject the null hypothesis. Reject. We don't reject it because although X bar is a little bit different than that, it's not exactly there, it's plausible within the scope of variability that you could do something like that if it really was X bar. So you can't convince me or other people that that's not true. It might not be true, you might still suspect that it's not true, but you haven't proven it. Yeah.
Can you go back a slide real quick?
Yeah.
And scroll down.
So at this end, it just says, compare this distribution we've simulated to the original X bar. And if it's out there, way beyond, then it's going to be unusual. This is Matt, yes.
And that's just, the rejection area is just determined arbitrarily by whatever.
Well, so it's under that sampling distribution, right? So it could be different, right? Depending on the statistic and the sample size and the distribution of the underlying, it's going to adapt to the scenario that you have. But, usually if it's out in the 5% tails, that would correspond, called a significance level of 5%, then it's unusual, then it's considered kind of unusual. So if you're doing two-sided, it's just not equal to that. If it's in the upper 2.5%, so if we had 1,000 intervals, 1,000 different X bars, if it's in the top 25 or beyond, right? The top 25 or bigger, or the lower 25 or bigger out of 1,000, that's getting out there to be kind of unusual, right? And so if you set up a standard, if it's out in the outer 2.5% on either side, we're going to reject 50. That would be called a significance test with a significance level of 5%, meaning that you're going to reject if it's out that point. We'll talk a little bit more about interpretation of that, but that's the general picture. So let's look at this just a little bit more on the computer. So in these cases, we're way out there. Right? Let's look at a different example. This data set also has heart rate in there, and there's males and females. I think the sex one is male and the sex 0 is female, but I didn't find my notes when I looked. But there's a slight difference in heart rate of individuals who are admitted to the ICU. Right? This is calculating the two heart rates separately. This split command can do them at once. So there's this difference of about 2 beats per minute in these individuals. And again, these are people admitted to the ICU, so maybe that's a little bit higher. This is the box plot of the individual values. So some heart rates are kind of low, below 50, some are pretty high. Right? This is the averages for the two groups, are those two red lines. Right? There's not that much difference between the averages, kind of relative to the scale. Are the heart rates among males and females really the same on average, or is there a difference? Right. So we're going to set up a null hypothesis saying that the heart rates among individuals admitted are the same. Right. So in this case, our next example, heart rates. We have men and women. F mu sub m is the average heart rate for the men, and you can use W is the average heart rate for the women. The null hypothesis says no difference. Right? That's how we set that up. Use of M equals mu sub W, or that can be translated into mu sub M minus mu sub W equals 0. You can subtract the other way, of course. The alternative that we're going to entertain now is just that they're different. There's a difference between these groups. Maybe on this question is not quite as, well, it's an important question, but you could imagine asking any number of things. Right? Are there differences by age groups? Are there differences by race, ethnicity groups? Are there differences by time of day? If somebody comes in the middle of the night versus during the the daytime, maybe there's a difference in there. So the alternative is that there is a difference, so this one is no difference, and this one there is a difference. And for now, we're not specifying as higher or lower. Usually without kind of an a priori setup where you're really investigating something, you think it's going to go one way or the other, then you're going to get that, right? So the data that we're going to have, we have a sample size for the men, a sample size for the women. We have an average for the men and an average for the women. We can also get standard deviations for these groups. We can get standard errors. So there's a lot of different summaries that we're going to do. And what we're going to summarize, look at as our statistic is x bar m minus x bar w. It's going to be the statistic to use in testing. And we're going to decide whether to keep entertaining this assumption that they're equal. Right? Based on the sampling distribution, not necessarily these individual ones here, but really the sampling distribution of this difference. Right? So we're going to look at the null value. mu sub m minus mu sub w. The null hypothesis says it's 0. We're going to, when we have our data, x for the men, x for the women, and the average for the men, and the average for the women, we're going to adjust this. We're going to adjust these data and call them y's. So that the average of the two groups is equal to 0. I mean, is equal to one another. Right? So we're going to modify the data slightly so that it's consistent with that null hypothesis, and then generate bootstrap samples. And then we're going to have a picture of that sampling distribution. Bootstrap samples are going to show us the sampling distribution. And if our actual x bar for men versus x bar for women is out here, if it's really far away from 0 relative to that standard error and that sampling distribution, we're going to reject. On the other hand, if that small difference we saw does in fact fall within a plausible range here, right, then 0, even if it's not really true, I mean, it's plausible, we can't reject it. It's not, we would say it's not statistically different than 0. So let's see how it works out. For this one, do you think we're going to reject? And these are the box plots, and there's where the averages are. Well, it's pretty close, right? So we're going to create an adjusted variable, HR equal. That's going to make the mean equal in these two groups, right? So I'm going to adjust the one when sex equals 1, so that the average of the men is the composite average. And I'm going to adjust the heart rates for the women so that their composite is the thing again. So just a little bit of adjustment there. Right. The means in both of those groups now when they're adjusted is 98.95. The box plot, you see that little lip there? My little adjustment made that difference there. I'll run the next command. That's where the composite line is. All right. So I just adjusted the data even a little bit to make them equivalent under the null. Now I'm going to bootstrap. Right? Call it boot2 because it's the second example. HR random. I'm just going to randomly associate the heart rates. Right? Just mix them all up. And the ones that before were labeled, you know, the rows 1 through 100, 1 through 200. Some of them are labeled as men and some of them labeled as women. If there's really no difference in these distributions, I can just mix them all up and call one group men and one group women, and there's no difference. There's somebody just thinking about that, you know, these bootstrap things, these randomizations. How do you make the data consistent with the null? How do you express in this randomization there's no difference? If I take all 200 heart rates and just mix them up and give some to the men and some to the women, that on average should be 0. Right? Sometimes the men get the higher ones, sometimes the women get the higher ones, and vice versa. Right? So that's doing that. Then I'm going to take the mean when the sex is 1 versus the mean when the sex is 0. Get back here and run it far enough and then back. Now that histogram of averages looks like this. The line that is at 0, of course, is right in the middle because that's where I've set it up. I've tried to do the simulation under there. Where does the other one show up? The other one shows up here. The actual difference between men and women was a few points, a couple of points, right? So does that X bar difference, right, the red one, does that look particularly unusual under this distribution? No, it's quite practically in the middle. It's not out in the tails as representing an extreme allocation among men versus women. It's not in the lower one, which would imply the other direction. It's pretty close here in the middle. Now if we calculate how many times did we get a simulation that's actually above that, that's going to give us a probability, a number, right? And it's not extreme. It's not extremely small. So in the bootstrap, about half the time is above 0 and half below. This number here you can't see, but about 70% of the time, let's see, that first one, it's below, and about 30% of the time, the random association average difference is bigger than what we actually got. So 30% is not really so unusual. Right? If it really were 0, we'd get something as big as we got, or bigger, at least about 30% of the time. It's not really surprising, unusual to get something that big, or even a little bit bigger. So in this case, we have this sampling distribution. So to make it, some people call this a null distribution. Some books call it a randomization distribution. Either way, it's a distribution of a statistic assuming that H0 is true. So this is where H0 is true. The average for the men minus the average for the women is 0. Right? Our actual value ended up being about here. There was about 0.29 or 0.30, depending on how you round it, probability being above. So that's really 290 out of 1,000 samples, bootstrap samples. Had y bar min minus y bar w greater than or equal to the actual 1. And remember, these were the adjusted data that went into making that histogram. So it'd be very plausible if it was 0 to get something at least that big. Right? And so because of that, because this is not small, it's not 1%, it's not 2%, it's not an unusual thing, we conclude do not reject H0. It's plausible then, or it wouldn't be unreasonable to act as if they were equal, and that's not an important difference. So you can say it's plausible that the averages are about the same. So you don't really, don't reject in that case. But any questions? To the point of, I think, of presenting it this way with the simulations and generating data and seeing is something simulated under the null hypothesis, similar to what you actually get, right? Is kind of at the core of this idea of a sampling distribution. Do this. We're going to come back to this on Friday with some formulas. All right, we're going to use t-distribution. We're going to calculate, assuming that there's a distribution here. We're going to do it instead of a z-score. We're going to standardize something and then compare that to a t, and calculate the probability under a distribution. Right. But at the core, it's comparing things that you might have seen had the null hypothesis actually been true to what you actually got in practice. And if you're not unusual, given your sample sizes and the distribution underlying of the data, if what your result that you actually see is not unusual, you don't reject. But if you do get something that's really quite unusual, corresponding to a little tiny probability area under there, this tail area here is related to what's called a p-value. Right? And if the p-values are small, like 1%, 5%, something like that, then we reject. So if you're out in the extreme. So keeping in mind this, because it's kind of a little bit different than confidence intervals. Confidence intervals are a little more straight. Here's our estimate. We think if that were the mean, we'd have a plus or minus standard error, and that's kind of where we'd be. Right? This one says, well, if you'd been over here, you would see things like this. And if you're in the reasonable range, if your actual results are in the reasonable range under what hypothetically would have been the other thing, then you can't reject that thing. But otherwise, it's extreme. Right? Yes, and we can make errors both ways. Sometimes you reject things that are really true because you get an unusual sample. More often than not, though, you don't reject because your standard error is too big. Right? And even though there might be truly a difference under there, you just haven't, you don't have the data, enough data to show it. And the sampling distribution is too wide relative to that. Or in actuality, the effect is pretty small. Right? So if you're doing something to lower blood pressure, and it only lowers blood pressure by 5 points, that's pretty small in terms of the overall variability of that measure. So it might be pretty tough to prove that it's statistically different. Yeah.
So, like thinking outside of like the health and sciences, say
Yeah.
you take this to like a financial field.
Mm-hmm.
So how could that be applied into a financial field, like predicting?
Well, so say you had an example where you're a company, right, and you have your customers, and you have two different groups of customers, and you're looking at something. Maybe you have 100 people here, and you have 200 people here, and there's a certain rate of buying add-on products or returning to renew, or for quantity bought. Right, so X bar 1 could be something like dollars spent in that group, and X bar 2 could be dollars spent this way. And so maybe you're interested in which group, is there a significant difference in how much they spend? Maybe they get advertising campaign 1, advertising campaign 2. And say this is, $105 and this is $125. But this advertising campaign actually costs more, right? It's more involved. It uses a different technique. And you see these differences? Is that a real difference of $20? Is that, or is it plausible that really it's the same? And you just seen one sample that is a little bit off from equal.
Gotcha.
So if the sampling, it would depend on what the distribution of X is. If X is really hugely variable, it might not be enough to say conclusively that one is doing better than the other. But if the standard deviation of amount spent is, if everybody's spending between, $0 and $300 or something like that, it might be very plausible that the standard deviations are moderate, and then there's a significant difference between the two things. It could justify a different plan in business based on testing. So we'll come back on Friday and do more with the formulas to put things in, but underlying is this logic and my mistake. And I'll pick up the homework 6. Mention that to me.
I worked on it with you.
Yes,
I guess
yes,
I
yes.
just never officially turned it in.
Okay.
But I've had it the whole time.
Okay.
So
I do remember we're trying to take it and look at it, and then
Yeah.
and then
I just noticed I had it here, and I was like, I know I did that once. I did it with you. So
Yeah, right.
I guess I forgot to put it in my phone.
Good. Well, thanks for bringing it up. Thank you.
Okay, Sharon, here. There's a product. Good day.
Good. Thank you. Thanks.
Thank you.
Great. Thanks.
I also, so are you going to be in my senior seminar in physics? I'm going to be looking at pipe junctions and branches
Okay.
and how the fluid flow
Oh.
relates to maybe trying to come up with a model for
Yeah.
that. And I was just wondering if you could think of maybe a way that I could get multiple data points for like putting fluid flow through something like
Yeah.
would I just take pressure readings over time and then see those data points?
Yeah, I
I don't know if
guess
you've
so.
ever seen anything
So
similar.
you'd have set up some type of apparatus to measure
Yeah.
pressure and, if you changed flow coming in or flow at an end, you could do analysis with different
Okay.
points or.
Yeah, because I was just wondering, because I'm not going to print up, 3D print, multiple versions of the same thing, because that would just take forever, so.
Yeah.
I don't know if you had ever seen anything like that.
I don't have a specific example in mind, but we could talk about it more.
Yeah.
Once you have the design, but whether there'd be different type of substances you would send through there, water, something with chlorine in it, or something with some other chemical in it that would kind of affect the flow.
Yeah.
And you could see multiple times, run it through multiple times and look at it.
Because my first thought was just to kind of set it up, run it, set it up, run it, set it up, run it,
Yeah.
and then, but I didn't know if I just kind of keep getting the same results, if I have the same initial setup.
There'll be a little bit
So,
of measurement
yeah.
variability, or just, doing cold water one time, hot water another time. If it's, think about the pipes going through a house, some of them are flat, some of them are going up, some of them are, So do it once where the mechanism has to go up and then down, and so you would, if, you might not get a whole lot of variability within one set of conditions, but do all the water first, so it's kind of clean, and then do it with oil or something, oily water, and see if it makes much of a difference. And so it might kind of gum up your
Yeah.
thing that you
The
make, or you
device,
run
yeah.
too much through there, but it could get some different values to look at. And if you do it, say, 5 or 10 times for each type, you could do a comparison of those. So, all right, yeah, so just kind of thinking about different scenarios like that. Okay. Yep.
Thank you.
Well, there's a question for rating for that. I'm sure I'm
What is the probability that a single truck's processing time is between 12 and 15? So if it's just a normal distribution with mean of 13 and standard deviation of 4, right? So that's just going to be using a normal and doing a z-score, right? So 12 minus 13 is a mean divided by 4,
Oh, just the regular.
just the regular interval. And then the later ones is an average of 16.
Yeah, I know.
trucks,
Yeah, I know the ones.
Yep.
So it'd just be so what is it? 12 minus 13. So just 12 minus 13 over this 4.
Yep, and the other one was
15. Here's the.
Okay, thank you. Yeah. How are things going?
Good, pretty good.
Basketball season.
Yeah, we finished. We got done like last week, so now I have pretty a lot of free time. That's
Yeah.
good. I can't
You can sleep in a little bit more.
Yeah, and also just like I have more time to like do homework and stuff.
Yeah. But you're keeping up with this one? and doing
Yeah,
very
yeah,
well,
this
so
was, yeah.
Good.
I'm doing bad, yeah. All right, have a good one.
Hey, Garrett.